on cue this morning, I guess, this morning. So you have a quiz on Monday. It's going to cover the remainder of the bash stuff that we didn't cover on the first quiz. So some regular expressions, nothing, so this is here, but it's nothing obscure, right? I'm not going to try to give you a regular expression that you can't figure out or ask you to write a regular expression that's basically impossible to write. Right, so don't expect anything that's really difficult here. There's some arrays. Obviously, if there's arrays, there's loops. Yeah, I'll be with you in a second. There'll be functions. And then there'll be a little bit of C, but not a lot. Right? I don't know the format yet. I haven't quite settled on the quiz yet, but it's going to be, I suspect it'll be similar to the first quiz. Question?
Yeah, in the assignment, when you're using the find method with regular
Yeah.
expressions, alternatives, and we're using that, so when we're doing regular expressions,
Yeah. I mean, yeah, so the assignment would be, that'd be about the hardest regular expression I'd ask you to come up with. Okay. All right, any other questions about the quiz? Okay. So I mean, you should expect something similar to what you got for quiz 1 in terms of difficulty and length and so on. All right, so today's lecture, so it's 2 parts. So part 1, we're going to use some structures. We're actually going to create a data structure and create something that sort of resembles a Java class. And so that's, so the topic of this is called organization of a C program. All right, so in the previous lecture, we had this structure called point 2. Right? So point 2 represents a 2-dimensional point, right? Similar to the point 2 class that you saw in CISC220. Now, whenever you create a type, or a structure like point 2, right, it's often the case that you want to do something with the structure, right? So I want to compute something that involves points, right? And that typically involves creating a bunch of functions, right? Because you're not supposed to repeat your writing code over and over and over again, right? Now in Java, you know how this would work, right? You make a class, you put the fields X and Y inside the class, and then you add a bunch of methods to the class, right? So in C, that doesn't work because there's no classes in C. Right? And so what you end up doing in C is you end up doing, I guess, an approximation of that. So what you do instead is you create something called a header file. Right? So your header file contains the declaration of your structure, right? Possibly. And then it contains a declaration of the functions that you want to operate on the structure. Right? So it's only the declarations, right? It's not the definitions. Right, so declarations, but not definitions. Right? So you put these in what's called a header file. Your header files normally have this extension .h. Right? So in all of our, whenever you include standard io.h, you're including a header file. Right? So now we're going to write our own header files. Anybody that wants to use your type can just include the header file. Right? Eventually, they have to link to your compiled type. But to write code using the type, they just have to they just have to include the header file. All of your definitions, so your function definitions, possibly the structure definition, goes into a source code file, so into a .c file. Right? So you split up your implementation into 2 pieces. Right? There's a header file, and then there's the source code file. Right? The header file contains all the declarations. The source code file, the C source code file, contains all of the definitions. Right? So with that point 2 structure that we had in the last class, we can create some methods that operate on point 2 objects. Right? So for example, I can move a point 2 object by some amount x and y, right? dx and dy. Right? So that's just adding dx and dy to px and py. Right? I'll explain why you need a pointer here in a moment. Right? Similarly, I can write a method called multiply, right? That takes a point, multiplies it by a scalar s, right? So multiplies the coordinates of the point by s. Right? I can write a function that tests if 2 points, p and q, are equal. Right? Do they have the same coordinates, x and y? Right? And then I can even make a function called toString that returns a string representation of a point in case I want to let somebody print that point. Right? Now, why does this function here take in a pointer to a point 2 structure? Right? Well, the answer is it's going to modify the object that P points at. Right? So remember, if you want to change, a variable belonging to a caller, right? You need a pointer to that object, right? You can't just pass in the object itself, right? Because what you end up with is a copy of the object inside the function, right? But if you pass in a pointer to the object, you can actually modify the state of that object, right? So anything that needs to modify the state of a point is going to take in a pointer to a point, right? Equals does not modify a point, right? So here it takes in just 0.2. This actually, now that I'm looking at this slide, this is actually, the const here is unnecessary. I'll explain what that does in a second though. Right? Similarly, toString does not modify a point. Right? So you can just pass in a regular point 2 here and not a pointer to a point 2. Now, you might wonder what const is doing here. Right? So const I haven't told you about yet. Somewhere I have a web browser. Where is it? Here? Okay. And there it is, const. All right, so what does const mean when you label a variable const? Right? So const is what's called a qualifier in C. Right? So you can qualify, when you declare a variable, you can qualify it as being const. Right? Now notice here, okay, objects declared with the const qualified types may be placed in read-only memory by the compiler. Right? So what this is trying to tell you is if you declare something const, that variable is effectively read-only. Right? So you declare it const, you give it a value when you declare it, right? And then you can't change its value ever again. Right? Sort of like final in Java, but not quite the same thing. Right? Remember, final means in Java you can assign a value to a variable once. Right? Const means that the value of the variable is readable only. You can't write to the variable. Right? So here's some examples. Right? Here we've got const int n equals 1. Right? What does that mean? I have an int, a variable called n. Its value is 1, and it's const. So it's the value of n never changes. Right? So in fact, so the value of n is always 1 in this case. If you try to assign to n, right, the compiler issues a warning. An error. Sorry, the compiler issues an error. Right? You get some error saying the type of n is const qualified. You can't write to it, right? You can't assign a value to it. Now what happens with if you take a pointer to an object? Right? So here we've got int x equals 2, right? So x is just an int. It's not const, so I can change its value. Right? On the next line, we've got a pointer, right? So we have a pointer int star, right? So we have a pointer to something called p, right? And we're going to make it point at x, and we're going to label this pointer const. So when you label the pointer const, that means you cannot change the value of the object through the pointer. Right? So you can't change the value of the object through the pointer, even though the object itself is not const. Right? The object itself is not const. However, you have a pointer to const, which is how you read this. Right? So a pointer to a const object. Right? So if you try to assign through the pointer to that object, that doesn't work. Right? And here we've got a structure. So this is declared in a bit of a funny way. We haven't seen this yet. So here we have an unnamed structure, right? So it's a structure that doesn't have its own name, right? Inside that structure, we have two members, right? We have int a, and we have int b, but int b is declared const, right? So we have a structure. One of its member variables is constant. Now this funny syntax here, so when you make a structure and you don't give it a name, you can make a variable right after it. Right? So here there's a variable of, whose name is s1, and its type is one of these structures here. Right? I would discourage you from using this syntax until you're used to working with structures. Right? So you should do it the way that I've been doing it there instead. Right? So here we make a variable s1. Right? It has a member A and a member B. Right? B gets assigned to 1, gets the value 1. Right? Here we've got S2. Right? B gets the value 2. Right? And A in both cases is 1, 0 in this case. Right? It's A is a member of a structure. It hasn't been initialized yet, so it gets 0 initialized. Okay. Now notice that The member B is const, so you can never write to it. Right? So if you try to write S1 equals S2, that fails in this case. Right? Again, the compiler says you can't do this. Right? Because to do this, what the compiler has to do is it has to do S1A equals S2A and S1B equals S2B. But the problem is S1B is const. Right? So you can't write S1B equals anything and have it work. Right? So that doesn't work either. So const means, so a const qualified variable means the variable cannot be written to after you initialize it. Right? So that's all that means. Now, in the example here now that I'm reading it, this const doesn't actually do anything in this case. Right? All this does is make sure that you inside the function, if you write p.x equals something or p.y equals something, then the compiler catches that as an error. Right? All right, so we've got our functions. These are the functions that we want to create. Right? So we're going to put these into a header file. Right? Let me skip over. Oh, well, I guess we'll. OK, so when you create a header file, right, normally the first thing that you do is you put in what's called an include guard. Okay? So that you decide, OK, I need a header file. The very first thing you do, write an include guard. Right? So an include guard prevents the header file from being included more than once in the same source code file. Right? So if you accidentally include the same header file twice, you want to avoid it from being included the second time. Right? And that's what the guard does. So traditionally, the way that you implement this is as follows. Right? So you use what's called a preprocessor directive. Right? So you've seen include. Now the next preprocessor directive that we're going to use is if-end-def. Right? So if-end-def means if not defined. Right? So .2h, that's just a name of some, that's just a name. Right? So if .2h is not defined, right? So in other words, if this is the first time that the preprocessor sees .2h, right, then everything inside, everything from if-end-def to end-if, this will actually occur. Right? So if the preprocessor has not seen .2h yet, then the rest of this will happen. Right? So to indicate that the preprocessor has seen .2h, we're going to define the name .2h. Right? We're not going to give it a value. It doesn't matter. It's going to be 0 in this case, I believe. Right? So you just define the name .2h. Right? So the second time the preprocessor sees this header file, right, or tries to include this header file in the same source code file, right, this name .2h will be defined, and so it's just going to skip over to the end of the header file. Right? So there's your include guard. That's the thing that prevents a header file from being included more than once. Right? All right. Now the next thing that you do is you just put in the declaration of your functions. And here we're going to put in the declaration of our structure. Well, this is the definition of the structure. Right? So in the header file, we've got our structure .2. Right? It's got an x and a y coordinate. We've got our type def. Right? So .2 is actually shorthand for struct .2. Right? And now we've got our functions, right, as they were declared on the previous slide. Right? So when somebody includes this header file, what do they get? Well, they get the header file standard bool. Right? I need standard bool for bool here. Right? So whoever includes the .2 header file also ends up including standard bool.h. Right? Then they get the structure definition, they get the type definition, and they get the declaration of all of these functions. Right? You might wonder why the functions have these funny names. Right? So why are they called .2_move instead of just move? Right? And the answer is because in a C program, all functions have to have different names. Right? So if I just called it move, then there's a non-zero chance that somebody else is going to create a function also called move. As soon as you do that, so as soon as you try to include, as soon as you try to have two functions with the same name in the same source code file, the compiler barfs. Right? It says you've got two functions with the same name. You can't have that in C, right? Because there's no function overloading in C. So typically, when you create a data structure and you provide some functions to operate on the data structure, you end up doing something weird with the function names. Right? So here, because my type is called .2, all of my functions that operate on .2 have the, what's it called? Prefix, .2 underscore. right? So that's to prevent, or that's my attempt to prevent somebody else from creating a function having the same name. Okay, so anybody who wants to use the your point2 structure now can just include this header file. Right? But they still need the definitions at some point. Right? So the definitions, those go into the corresponding source code file. Right? So now there's a C source code file. So this is point2.c. Right? This is point2.h. Right? Point2.c, well, in point2.c, you're going to include your header file. Right? Because the header file has the structure definition, and it has the declaration of all the functions that I want to define. Right? So when you include a header file that you create or somebody else has created, right, the header file is included with double quotes. Right? So the name of the header inside double quotes, not the less than and the greater than. Right? So the less than and the greater than, those are only for the C standard library header files. Right? Anything that's not part of the standard library gets included using double quotes. Right? The reason is that because the C standard library files, the compiler knows where to look for them. Right? Here, the compiler is going to look in the current directory or where you tell it to. Right? Okay, and the next thing you do is you just define your functions. Right? So define the function point2move. So how do I move a point? Well, I just change px by dx, and I just change py by dy. Right? P is a pointer to a point2. So to get to the x member, use the arrow notation. Right? That automatically dereferences the pointer, gives you back the x coordinate of the point. Right? So I can just add dx to that. And same with py. Right? Again, because that's a pointer, right? To get to the member, or to dereference the pointer and get to the member, right? Use the arrow, and then just add dy to y. Right? Multiply is the exact same. Right? I'm going to multiply x and y by s. Right? So p arrow x multiply equals s, and p arrow y multiply equals s. Right? Okay, so what about equals? Well, equals, I want to compare px and qx and py and qy. Right? If they're both the same or both equal, then I guess the points have the same coordinates. Right? So, whoops. Right? So the slightly incorrect way of doing this is to write return px equals qx and py equals qy. Right? Why is it slightly incorrect? Because if px and qx are both not a number, then this is going to return false. Right? Because nan is never equal to itself. Nan is equal to nothing, not even itself, according to the IEEE floating point standard. Right? So this doesn't quite handle nan correctly, but the odds are if you're working, if you have not a number values, there's something else has probably gone wrong anyway. Right? If you want to handle them correctly, you have to put in an if statement that checks if they're both nan, not a number. All right, any questions so far? Okay. ToString. So creating the string representation of something in C is surprisingly difficult. It seems easy in Python and in Java, right? It does actually seem easy, right? In Python, in Java, you just write ToString. A lot of the time, you don't even have to write ToString, right? If you're going to print something out, you just print out pass print line a reference to a variable, sorry, a reference to an object, and then it magically calls ToString, right? What you probably weren't told, and probably what you never bothered to look up, is what exactly does ToString do for double? Right? So this is the documentation for the double class in Java. Inside that class is a method called ToString. Right? So this is the version of ToString that gets eventually gets called when you try to print or when you try to get the string representation of a double value. Right? So as a CISC220 student, right, you just write something ToString, or you just print line D, right, where D is a double value and something magically happened, right? A lot of stuff actually happened when you called print line, right? So this is what ToString does for a double value, right? So there's a whole bunch of cases here, right? If the argument is nan, the result is the string nan, right? Otherwise, the result is a string that represents the sign and magnitude of the argument, and then blah, 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 right? It just keeps on going and going and going and going and going and going, right? The generating the string representation of a floating point number is surprisingly hard, right? Notice that after the list, there's still another paragraph, right? So how many digits must be printed for the fractional part of M array? Well, blah, 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 right? It's not easy to generate the string representation of a double properly, right, or robustly. Okay, so we're not going to try to replicate this, right, because doing so, we'd spend the next week, and all you'd be able to do is print a double nicely, right, which doesn't seem useful. Okay, so I want to print out I want to give you the string representation, I want to produce the string representation of a point P, right? And so how do you do this, right? So what's a string in C? Well, it's just an array of car, right? So I have to make an array of car, right? I can't make a little local array of car, right? Because I want to return the string back to the caller, right? So I have to dynamically allocate memory for this array of car, right? So that's fine. So we know how to do that. That's just malloc, right? Part 2, how much memory do I have to allocate? So that's the part that's not quite clear, right? So the string that I want to generate is I want to generate something that looks like the following. So round bracket, the x coordinate, so like 0.1, comma, space, and then the y coordinate. So let's say minus 1.53, round bracket. Right, so that's what I want to do. So I need 1, 2, 3, 4 characters for the brackets, the comma, and the space. Right? So that's the 4. Right? Now, how big is that and that? The answer is we don't really know. Right? But if you Google for it, you'll find out that the answer is something like 15 or 16. Right? Something like that. This 15 is probably too small, actually, now that I think about it. Right? But it's something like 15 or 16. So you have to allocate a buffer of at least that big, right? You should probably make that something like 17 or 18. But anyway, it's fine, right? So that's my buffer size, right? So that's the size of the that's the amount of space I need in the array to hold the string that I want to return. Right? Okay, so now that I've got the size, I can go ahead and allocate an array of the appropriate size. Right? So we use malloc. Right? It's an array of car, so I don't need to take the size of car, because the size of car is always 1. Right? So I can just use buff size in this case. Right? So I've now got my array. Right? Now remember, malloc returns null if it fails to allocate sufficient memory. So check. Right? Is the buffer null? Right? So if not buff. Right? If it is null, then I've got a problem. Right? I don't have enough memory to store the string, so I'm going to return null in this case. Now next, I need to put the contents of my point into this buffer, right, into this string. So how do I do that? And so it turns out there's this handy function called sprintf. Right? So printf you know as formatted print, right? Prints to the terminal. Right? Sprintf does the same thing, but it prints to a string. Right? It prints into a character array. Right? So sprintf, I'm going to print into the character array called buff. Right? Now, what do I want to print into the character array? Well, the next part is the formatting string. Right? So I want a round bracket. Right? Then I want some double number. I'll explain what %g does in a second. Right? Then I want a comma. Then I want a space. Then I want another double number. And then I want a round bracket. Right? The two double numbers are px, right, and py. Right? Okay, so what does %g do? So %f prints a float, right? But when it prints a float, it does it in a very particular way, right? There's another way to print a float, so that's with %e, right? So that uses what's called scientific notation, right? So that's 1 point something e to something, right? So if you don't remember what it is, if you have like 1.0 e to the 3, that's equal to 1.0 times 10 to the 3. Right? So that's scientific notation. So that's what you get if you use %e. %g tries to pick the best of %f or %e. Right? So if the number is very large, it uses scientific notation. If the number is reasonably small, it uses the regular %f notation. Right? And so that's what %g does here. Okay, so what does printf return? Right? So it returns the number n, right? So the number n is the number of conversions that were successfully performed. Right? So here we're asking printf or sprintf to perform 2 conversions, right? One there, right? Sorry, printf, not the number of conversions, hang on. You always have to look this stuff up. So sprintf. I guess this one works. Oh wait, it was right there. This is the one I want. Okay, so sprintf right here. Number 3. Writes the results, the behavior is undefined, and then where does it return? Oh, you'll also notice the following, right? So whenever you read Javadoc, right, the Javadoc is structured really nicely, right? Like it's really easy to read things in Javadoc. C has no standard way of documenting stuff. And so you're kind of stuck with whoever wrote the documentation that you're reading, right? And so here, you've got to learn how to read cppreference.com, their way of documenting this function, right? And so here you have to, once you get used to it, it's not that bad. But it's a lot harder than reading Javadoc. So somewhere you have to poke around and find, here it is, the return value. Okay, so the return value for number 3 is the number of characters written to the buffer, right? Or a negative value if an encoding error occurred. Okay, so number of characters written to the buffer. All right, so sprintf, right, returns the number of characters written to the buffer. So if n is less than 0, it failed to convert px or py for some reason, which would be unusual, right? If n is greater than or equal to the buffer size, right, I have a problem, right? Because I've either overwritten the buffer, right, or I've written everything into the buffer, but I haven't written the trailing /0, right, the terminator for the string, right? So here I'm going to check whether or not sprintf actually managed to write the coordinates of that point into this array properly, right? If I didn't write it into that array properly, I'm going to free the memory that I used because I haven't produced a usable string, right? And then I'm going to return null, right? If this succeeds, I'm just going to return a pointer to the array, right? Or buff in this case. Yeah?
Isn't it being echo is what we want?
Sorry?
Isn't it being echo and echo buff?
Yeah, so see, this is the thing in C. You have to read the documentation exceedingly carefully. The number of characters written to the buffer, not counting the null terminator character, right? So this is a very easy mistake to make, right? Very easy mistake. Suddenly, and now if you return that string back to the caller, right, they get back a character array that's missing the null terminator. As soon as they pass that to a function that takes in a string, that function barfs. And then suddenly something bad happens. So lesson number 2, right, when you read the documentation for, well, lesson number 1, read the documentation. Lesson number 2, you have to read it exceedingly carefully, right? Because the language is brutal. It's brutal. It will do exactly what you ask it to do, and that's all that it'll do, right? So if you didn't notice that it doesn't count the null terminating character here and return that string back, there's a good chance that whoever gets that string is going to run into problems when they try to pass it to a function that actually takes in a proper string. Yes?
Can you explain again why do we have to check for n bigger or equal than buff size?
Yeah. Okay, so remember that in C, whenever you have a string, so a string in C is just a character array, right? So I have an array car, C, square brackets, right? Oh, let's do this, C4. Okay. So that buffer, or that array, can hold a string of length 3 because the last character in the string, right, the end of the string has to be marked with a /0, right, the null terminator. Right? So I can do C0 equals a C1. I guess I should have made this shorter. Sorry. C2 equals C. And then C3 /0. Right? That /0 has to be there. Right? If that /0 is not there, then that's not a string that any of the standard library string functions can handle properly. Right? So that thing has to be there. The length of this string is 3, because when you calculate length of the string, you don't include the null terminator. Right? Now, notice what the documentation for sprintf says. It returns the number of characters written to the buffer, not counting the null terminator. Right? So if I had that buffer C, right, I use sprintf, and sprintf gives me back 4, right? That means it wrote something into C3 that's not that, right? Yeah, so that's a problem. Right. Okay, lesson number 3, trying to generate the string representation of anything in C, especially if it's a floating point value, is a pain in the butt, right? It's not easy to do. Yes?
What if you write if m equals buff size -1? Wasn't that like better?
Yeah, if n, sorry, run that by me again?
Like for the n smaller than 0 or n.
Yeah.
Like, instead of that, just write n equals buff size -1.
Equals buff size minus 1.
Or like,
So buff size minus 1 is okay, right? That's okay, right? That's because that means
that's what we are trying to get.
yeah, but this is checking for the error condition. So this is checking for the condition where it didn't work. Yeah, yeah. Okay. All right. So yeah, so I guess the other lesson is, right? There's a reason why Python and Java are popular as languages, right? When you want to print something in Python or Java, you don't worry about it. You just print, right? Or use print line, and then in Java, toString takes care of things for you. In Python, some function takes care of things for you, right? In C, there is no function to take care of anything for you, right? You've got to do everything on your own. Okay, so that's the structure of a C program, right? Of a very simple C program, right? So that was a very simple data type, right? When you make a data type, typically what you do, you separate it into 2 pieces, right? The header file includes perhaps the structure that defines your data type, right? The functions that you want your data type to have. All of the implementation goes into another file, right? Into the source code file. Right? And that's the usual way that that any non-trivial C program looks like, right? There's a header file and there's a C file. There's multiple header files and multiple C source code files, and they're all stitched together to form one big program. Yes?
Question for the buff size.
Yep.
You have +4 for the bracket.
Yep.
And space bracket.
Yep.
What happens? Do you need another space for the backslash?
You do need another space for the backslash 0.
Okay.
Yes.
So it would be +5.
Should be +5. Yes. That would be the correct. That would be more correct. Yes. Any other questions? Don't be surprised if you find bugs on my slides. It's an easy language to make mistakes in. All right, super. Those were all very good questions. Next lecture. Okay, so we implemented a very simple data structure. I now want to implement a more complicated data structure. Right? This one using arrays. This one using an array. All right, so if you're in 124, this is all brand new to you. Right? If you've taken 124, this should be a review. Right? So what we want to do is we want to implement an array-based list. Right? So in Java, that would be the equivalent of ArrayList. Right? Now, what does ArrayList do? It's a resizable list. Right? The way it's implemented in Java is there's an array that actually stores the elements of the list. Right? But you know in Java, you can keep on adding stuff to the list, and the list just grows as required. Right? And so the problem that we're going to have to solve here is that we're going to have an array to store some elements. Right? If we add too many elements to the array, right, we have to expand the size of the array somehow. Right? And so that's the problem that we're going to need to solve when we implement this data structure. Okay, so there is a zip file on OnQ that has the source code for all of this. I'm probably not going to get to the source code in the next 15 minutes. Right? So we're going to do exactly what we did for point 2. Right? I'm going to make a header file that includes how we're going to structure this list and includes how all of the functions that we're going to write for this list. We're going to put the implementation into a source code file, list.c. Right? This is only going to work for int elements. Right? So I can make a list of int, and that's it. Right? We're not going to make a generic list that can hold anything. Not yet, anyway. So we're going to need some functions that we haven't seen today yet. Right? But we're going to look at those probably in the next lecture. Right? OK, so what's a list? A list is just a sequence of elements of a single type. Right? You know that the elements, they all have a position, right? An index. So 0, 1, 2, up to n minus 1, right? Where n is the size of the list. Right? So the size of the list is the number of elements in the list. Right? Now, if we have an array, right, the array can hold a fixed number of elements. Right? The size of the array is not the size of the list. Right? So I can make an array of size 20, right, but the list might have 0 elements in it. Right? So the size of the list is not the same thing as the size of the array. The capacity of the list, that's the maximum number of elements that can be stored in the list. Right? So the size of the array defines the capacity of the list. Right? The maximum number of elements that you can store. Right? Whenever you add an element to the list, right, in our implementation, we're going to add the element to the end of the list. Right? So if I add to the empty list, then there's an element at index 0. Right? If I add to that list, there's now an element at index 1. And if I add to that list, there's now an element at index 2. Right? And so on and so on and so forth. Some lists add at the front. So they grow from the front. They grow to the left. Right? Our lists are going to grow to the right. Of course, when you add an element to a list, the size of the list grows by 1. Right? Now, you can implement just a fixed size list, right? So a list that has a maximum size, right? And that would be perfectly acceptable in a lot of situations as long as you know how, as long as you have an idea of how big a list you need, right? But it's often convenient that the capacity of your list grows or shrinks possibly as required. OK, so here's an empty list, right? So I'm drawing the array, right? So the array has no elements in it, right? But in C, the array always has elements in it, right? So here we have a capacity of 8, right? Our size is 0, so there's no elements in the list, right? Our valid indexes is, well, there are no valid indexes, right? If there's nothing in the list, then I can't index the list to get an element, right? The list of size 1, right? Here I still have capacity 8, right? So I can hold 8 elements in this array. There's 1 element in the list, right? The only valid index here is 0, right? I add 1 more element, right? So that has that's an array. That's a list of size 2, right? Capacity is still 8 because I haven't changed the array yet, right? And my valid indexes are 0 and 1, right? Okay. So if I add a bunch more elements to the list to fill up the array, right, then I've got a full array, right? So the size of the list is 8, and the capacity of my array is also 8, right? My valid indexes are from 0 to 7 in this case, right? OK, so I've got a full array. Now I can go and, well, I've got elements in the array, which means I can get and set different elements of the array, right? OK, so when you get an element, right, that returns whatever value is stored in the array at the specified index, right? So if I get the element at index 3, that should return the array the element that's shown in yellow, right? Now, when you set an element, number 1, there has to be an element there, right? So back here, I cannot set element number 6, right? You can only set an element that's already in the list, right? So set is equivalent to replace. Right? So setting the element in index 3 changes whatever the value is that's stored there. Right? The reason you can't set, say, the element at index 6 here is because then you have a list that's got a bunch of free spots that have nothing in it. Right? And it's not clear how you should deal with that situation. Right? So you can only set an element, you can only set an index that already has an element in it. Right? So you always get undefined behavior if the index is invalid, right? If I try to set or get that element there, well, that element doesn't exist, right? So I can neither set nor get it, right? In C, well, we have to decide what is it that's going to happen if we try to do that, right? In Java or Python, you would get an exception, right? In C, there's no exceptions, so we have to do something else to indicate that an error has happened. Okay, now if I have a full list, right, and someone wants to add to that list, right, then that means I need to, if I want to be able to grow the size of the list, right, that means I have to take this array and replace it with a bigger one, right, because I need more space to hold the element, to hold the next element. Right? So in a resizable list, adding an element to a full list causes the list to resize its storage array. Now, when I resize the array, I've got to copy all of the elements from the old array into the new array. Right? Finally, if I'm going to resize this array, right, I need a strategy on how I'm going to resize this array. Right? So should I add one more element to this array, or should I do something else? Right? So it turns out you should do something else. Right? You shouldn't grow the array by one every time. It turns out that's the worst thing you can do. Right? So it turns out what you should do is you should multiply the size of the array by some factor, by some factor of the current capacity. Right? So in other words, I should double the size of the array, or I should multiply or I should make a new array that's 1.5 times bigger than the current array. Right? It turns out if you do that, that has some nice complexity guarantees. Right? If you just increase it by 1, that has a very bad complexity guarantee. Right? So our strategy is we're going to double the capacity of the array when I need to. Right? Now, I want to add one element to this array, so I'm going to double its capacity. So now I have an array of size 16. Right? And then I can go ahead and add the new element to the end of the array. All of the previous elements, right, I'm going to put into the new array. Okay, now what about inserting into the middle of the array somewhere? Right? So I've got 9 elements in this array. If I want to insert at index 4, right, I don't want to set that index. I actually want to put a new element into there. Right? What do I have to do? Right? So it turns out what you have to do is I have to take those elements, right? Remember, I'm inserting at index 4. Right? So I need to take those elements and I need to shift them all one to the right. So I need to do that. Right? So that I can make space for the new element. Right? And so that's what the add method does in Java if you give it an integer value. Right? So add 4 and then some element. Right? That actually inserts into the middle of the list. Right? So we want to do that as well. Right? Inserting at the end of the list is usually allowed. So this is a bit odd. Right? So here so you know that the valid indexes are from 0 to 9. Right? But in Java, you're allowed to add to index 10. Right? So in Java, if you do t.add10 some value, it actually works. Right? So in other words, inserting at the end of the list is usually allowed, which is slightly unusual because the index 10 is technically not valid. Right? So we have to pay attention to that. It's easy to implement though. Right? If you detect that you're inserting at index 10, you just call your other add function that adds at the end of the list. Right? So you don't have to you don't actually have to implement a new function here. Well, you don't have to do much to implement this function. Okay, now what about removing? Right? So inserting, right? We have to shift a bunch of elements to the right and then add the element into the middle of the list. Right? Removing, so if I want to remove that element at index 4, right? I want to get rid of that. What I have to do is I have to shuffle all of the elements in red one position to the left, right? Because I want to get rid of this element here, right? So I want to move element 5 onto element 4. I want to move element 6 onto element 5, 7 onto 6, and so on and so on, right? So I want to shuffle those all over one position to the left, right? So you can see that in this implementation of our list, we need to move chunks of elements, right? Either left or right by one position. Okay, But how are we going to deal with bad indexes? So where's that thing here? Where'd it go? Here, right? So remember, if you use an index that's not valid, right? Here it says undefined behavior will happen, right? If you're providing a data structure and someone gives you an invalid, like a list, and someone gives you an invalid index, you should probably tell them that they used an invalid index somehow, right? So in other words, you should communicate the fact that an error has occurred, right? Now in C, believe it or not, there is no standard way to convey to the caller that an error has occurred, right? So one more time, there is no standard way to convey to a caller that an error has occurred. There are no exceptions in C, right? So what you decide to do here is kind of up to the implementer. So what we're going to do is we're going to use this thing called assert, right? So assert lets you assert that some condition is true, right? So here, condition is a Boolean expression, right? Something that's true or false, right? So if that condition is false, then assert whatever that condition is will cause your program to terminate, right? If that condition is true, your program just continues along its merry way, right? Now the nice thing about assertions is you can turn them on and off via a compiler option, right? So when you're debugging, you can put all the assert statements you want into your code, right? And then when you release your code, you can just leave the assert statements on in their code, and just when you compile your program, tell the compiler to disable assertions. So we're going to use assertions to indicate exceptional events in our code, right? And so that'll be our way to provide exceptions, given that the language doesn't have any proper exceptions. All right, so in the next class, we're going to actually look at the implementation of this list class.